Welcome to Coach Silver's podcast on equilibrium and net forces. This is one of the many ways you have available to you to obtain the information needed that you will use to complete a test on the date that I give here, which I have not given yet. If you fail to complete this or the other methods of gaining information, you will have to stay after school to catch up because we're going to be using class time to do other stuff. Also, if you get the chance on our website, where this video is found, you can also find links to these two videos, which are also very helpful videos. So let's get right into it. There is just a couple of terms that we need to know for this podcast, and that is force and net force. For what we're doing right now, a force is simply a push or a pull. You can push something, you can pull something, you can be pushed, you can be pulled. And the net force is the sum of all the forces on an object. You could be pulled in one direction and pulled in the opposite direction at the same time. And when we talk about force, we're going to use the word Newton, which is abbreviated capital N, and we will be talking more about newtons later on in this unit. This diagram is a very good representation of what is meant by force and net force. You have a block sitting somewhere, and if there is something that is pulling on it with a force of 5 newtons in one direction and something else pulling with a force of 10 newtons in the same direction, overall there will be a total force on the object of 15 newtons in that direction. In the case of this one below here, you have something that's pulling the object to the left with a force of 5 newtons and something pulling on it in the opposite direction with a force of 10 newtons. So overall that object is going to move to the right, and it's going to move to the right because there is a net force of 5 newtons acting to the right. In the case of the block on the bottom, you have 5 newtons going to the left and a 5 newton force taking it to the right, which equals out to be a net force of 0, and the object does not move anywhere. Two important terms dealing with force. One is called tension, which is a stretching force like what would be seen in the scale here, and weight, which is a product of mass and gravity and can be measured in pounds or newtons. Over to the right, there is a bag of sugar with a weight of 2 pounds acting down in this direction, and the scale, because of the force of tension, is reading 2 pounds, and that force, the tension force, would be directed upwards. A couple notes on the arrows that we're drawing. When you see an arrow, that represents a direction and a magnitude, which is how much of something. So let's say this arrow represents a force of 100 newtons acting down. If I were to draw an arrow like this, that's about half as long, this one might represent 50 newtons acting downward. So an arrow, this is also known as a vector, it has a magnitude and it has a direction. Anything that's a vector has both a magnitude and a direction, like force and velocity. Now some things can be added just like ordinary numbers. Those are called scalars. Those are things like measures of volume, measures of mass. Those are not vectors, those are what's called scalars. When we're dealing with forces, we're dealing with vectors. We need to know not only how strong it is, but what direction it's acting as well. Now that we know something about vectors, we can look at what's called mechanical equilibrium. Let's look at this in this example of these two dudes hanging out on a scaffolding painting. Let's look at the forces involved here. Each one of these people has mass, so they're also going to have a force, which is their weight. So let's draw that on here. Let's say that this person has a force of his weight acting down, and let's label that 100 pounds. And if this person, who looks like he's had a few more Twinkies than the other person, let's say that he is about 150 pounds. Now, are those the only forces acting on this scaffolding? No. The other force that's acting is the weight of the scaffolding itself, which is also acting downward. Let's call that, just for simplicity, 50 pounds as well. So we've got a total amount of force acting down of 300 pounds. I'm going to write that over here to the right. If this scaffolding is not moving, then that we can learn something about the total force of tension acting on the ropes. Mechanical equilibrium means that the sum of all forces equal 0. So if I have 300 pounds acting down, the total amount of force of tension in the ropes of the scaffolding must also be 300. So let's say that I am able to measure the tension in this rope or chain, and it is 225 pounds. That's what the scale is reading. Well, what can that tell me about the tension in the other chain? What that tells me is that that chain has a total tension of 75 pounds in it. You add 75 to 225, you get 300. Mechanical equilibrium. If the scaffolding is in equilibrium and is not going anywhere and there's 300 pounds acting down, there must also be 300 pounds acting up. If those forces were not balanced, the scaffolding would be either moving up or down, and it is not. It is in mechanical equilibrium. All right, here's a question for you. This is Newton-Nellie. She is going to be used a lot in examples coming up. Let's say Newton-Nellie. She is hanging by a couple of rings attached to rope. She's an aspiring gymnast. So, if she's hanging by two ropes, is in this case here, and they are both evenly spaced, and she's evenly spaced in between them, compare her weight, the force going down, to the tension in each one of the ropes. And then do the same thing for Newton-Nellie as she begins to hang with more of her weight supported by one rope than the other. Alright, and here's the answer, which hopefully you have figured out. But let's draw her weight as an arrow acting downward. And if she's hanging by two ropes evenly spaced from each other, each one of those, the total has to add up to the force going down. If they're evenly spaced, each one is going to be half of her weight. In this case, where she is supported more by her right arm than her left arm, her right arm is going to be more than half her weight in tension, and the left arm is going to have less than half her weight in tension on it. If you are not seeing this, go back and review, go back and read the beginning of chapter 2 and make sure you understand this. Alright, let's say you're standing on the ground or you're standing on the block on the ground. You are applying a force to the ground. That force is called your weight. It is a product of your mass multiplied by the gravity on the planet that you are walking on, which is more than likely Earth. Now, when you're applying your force down to the ground or an object you're standing on, all the atoms in that object are pushing back on you. And they are pushing back on you with exactly the same amount of force you're pushing down on them. That force is called the support force or the normal force. Depending on where you're reading it, either one of those words could be used. So if there is a weight, like is drawn here, that I'm outlining, pushing down with a certain amount of force, there is an equal and opposite force called the support force pushing back. So support force, normal force, same thing. They both oppose the force that an object is applying to something if that object is not going anywhere. Alright, now just because something is moving does not mean that it is not in equilibrium. Static equilibrium describes something that is not moving. But there is also what's called dynamic equilibrium. And in that case, something can be moving, but the sum of all forces are still 0. Here's what is meant by that. Here's a dude pushing a desk across the floor while doing what appears to be lunges at the same time. These lines here are to imply that the desk is moving. So he is applying a force this direction. The desk is moving in that direction. But it is not changing speed. It is going at a constant speed. The force of friction between the desk and the floor, which we're going to learn about in a later chapter, is in equal and opposite direction and magnitude to the force the guy is applying to the chair. So in this case, the chair is moving, but it is not changing its speed. The force that the man is applying is exactly equal and opposite to the force of the friction between the desk and the floor. So this is what's called dynamic equilibrium. The sum of all forces still equal 0, and the speed does not change. Now, this concept is something that might take further thought, but something that's moving can be in equilibrium. In the last example of the man pushing the desk, if he's pushing the desk and it's in equilibrium and he's pushing it at 1 meter a second, it's going to be going 1 meter a second now, 1 meter a second in 5 seconds, 1 meter a second in 20 seconds, 1 meter a second in 1,000 seconds, if it's staying in equilibrium. If at any time the speed changes and it starts speeding up or slowing down, it's not in equilibrium then. He might be applying a greater force and increasing his speed, or less force and it will be slowing down and eventually come to a stop. So equilibrium does not mean things are not moving. It means that they are not changing the state that they're in. It's in a steady state. It's the sum of all forces equaling 0. You can have static equilibrium, or you can have dynamic equilibrium. 2 questions that I believe are on your Unit 1 study map. So here's another question for you. An airplane is flying horizontally at a constant speed in a straight line, in a straight direction. Its state of motion is unchanging. In other words, it is in equilibrium. So they're telling you a couple things here that you want to make note of. They told you equilibrium. They also mentioned constant speed, straight line, no change in direction, no change in speed. 2 horizontal forces act on the plane. One is the thrust of the propeller, which pulls or pushes it forward. The other is the force of air resistance, which acts against the plane. Which one is greater? I hope that you said they are equal to each other. Your clues were the constant speed, the word equilibrium. If you had an airplane and you had thrust and run direction and you're told it's at a constant speed, the air resistance acting against the plane is the opposite direction. I'm going to spare you from having to see my drawing of an airplane on an iPad right now, and that part can be in your imagination. But if you are not seeing this, you need to go back and rewatch this video. Time for just a little bit more math, but nothing too bad now. Not yet anyways. So, you have 2 vectors that are parallel to each other. Let's draw this vector, and let's take another vector, we'll add them together. This vector plus this vector, you add those together, and you get just a longer vector. Pretty simple. Now, let's take the case of a vector going this direction, and a vector going this direction that's a little greater in magnitude. And in this case, if we take the sum of these, we can kind of consider this one here almost like a negative number, and then we're adding a larger positive number to it. The resulting vector is going to look something like this. Not as large as this one because we had a negative in either direction. It's kind of like if you had a -2 and you had a +4, you would end up with a +2. Basically the same thing with vectors here. And here we have an illustration of the think question from a couple slides back. If Newton Nelly has a weight, in this case they're measuring it in newtons of 300 newtons. If she's hanging by 1 rope, the scale is going to read 300 newtons. If she's hanging by 2 scales on 2 separate ropes, each scale is going to be half of her weight. If you were to take these 2 vectors and stack them end to end, it should equal this one. Alright, so I know what you're asking now. What if you had something like Newton Nelly connected to 2 strings at some unknown angle connected to 2 scales that weren't directly overhead? How could we figure out something about the tension in the strings? Well, I'm glad that you're thinking that because I'm going to answer that here using what's called the parallelogram rule. And here's how it works. First thing we need to do is draw a vector representing Newton Nelly's weight. And I'm going to draw that right here, acting down. Now I need to draw a vector equal in magnitude, opposite in direction, representing where the tension would be if the rope was directly over her head, which it is not. Now, what I need to do is draw on my math knowledge of what a parallelogram is. If you recall, a square is a parallelogram. A parallelogram is any shape where the opposite sides are parallel to each other. I'm going to take this arrow going upwards and the two strings holding her up and turn that into a parallelogram. Just like this. Now, if I take the portion of the string inside that parallelogram, like so, put an arrow on that, that represents the force, the tension on that string. It represents the direction and the magnitude. So again, using the parallelogram rule, I could figure out if this is how much force is needed to keep her up. I draw my parallelogram, and then that tells me how much force I have on each one of these strings relative to the normal force that would be needed to keep her up. Again, over here, let's say that this represents the force. Draw me a parallelogram, and there's my two force vectors. It's not giving me the number, it's just telling me relative to her weight, how much is on each one of those strings. Now here's a case where it gets even more interesting, because let's say that she's suspended by two strings on two scales, but the angles the scales make to the vertical are not equal. We can still use the parallelogram rule here, and that is what I'm going to do. Draw that. And then as you can see, the string on her left, your right, has much more force, of much greater tension on it than the string that is to Newton-Nellie's right, your left. So you can see the two strings and the relative amounts of tension in each using the parallelogram rule. There's one, there's the other, and that's the parallelogram rule. And this brings us to the end of this podcast. If there's anything you're confused about, go back and watch it again. Come in with questions in class tomorrow, and I look forward to seeing you then. Until then, may the mass times acceleration be with you. That will make sense soon.